Welcome guys to your 24th physics video, and in this video I'm going to talk to you guys about momentum in vector addition, because not only can you use vector addition when adding forces together, but you can also use it when adding momentum together to prove the law of conservation of momentum. It's pretty cool. And as an example, I'm going to talk to you guys about the pool example, because you remember a couple videos ago I said that whenever you guys were playing pool, then what you needed to do was you needed to hit the 8 ball into a pocket, and then whenever you do that, all of the pretty much energy and momentum gets transferred to the 8 ball from the cue ball. Well, the science was correct in that one, and we figured out the calculation, but it wasn't a really good realistic example of what happens, because in real life the cue ball keeps moving a little bit. So let me go ahead and show you guys a more realistic example. So say you have your 8 ball right there, and of course at first whenever you hit the cue ball, the 8 ball is just standing still. That's the one we want to put into a pocket. So before the collision, the 8 ball, since it's not moving, has a momentum of 0 kilograms times meters per second. Now the cue ball down here, I'll write a C on it. This is the one that's flinging across the table with a high rate of speed. So we'll just go ahead and make up a momentum for this, and as soon as you hit the cue ball, we'll say that it has a momentum of 10 kilograms times meter per second. Now what it's going to do is it's going to crash into the 8 ball, and hopefully this 8 ball goes into, whatever pocket you want it to. So whenever this happens, if you ever played pool in real life, your cue ball, after the collision, it doesn't come to an automatic stop. What happens is it rolls slowly away, and hopefully this 8 ball goes into a pocket like over here or something. So let me go ahead and show that. So this on the left hand side is before the collision, or as soon as you hit the cue ball. Now after the collision, it usually looks something like this. The 8 ball goes, we'll say the pocket you're aiming for is to the top right. The 8 ball goes flying over here with a high rate of speed, so we'll make a momentum like 8 kilograms times meter per second, and we'll say the cue ball, okay, that C's a little too big. Let me draw my ball first. The cue ball goes in this direction, and usually the cue ball ends up slower than the ball it hit. We'll say that this has a momentum of 2 kilograms times meter. Okay, that doesn't look like an M. Meter per second. And let me just symbolize the collision with this little bang right here. So again, what we're doing is we're hitting the cue ball, which had an initial momentum of 10 kilograms times meter per second, into the 8 ball, and a realistic result would be the 8 ball going in this direction at 8 kilograms meter per second, and the cue ball going in this direction at 2 kilograms meter per second. So how does this verify the law of conservation of momentum? Well, it verifies it whenever we look at vector addition. So let's go ahead and take a look at our initial vector. That is right here, and we can symbolize that by saying it has 10 kilograms per meter per second, or times meter per second. So whenever we add up the two resulting vectors, this one and this one, we should end up with the same thing as this initial vector. What the heck am I talking about? Well, let me show you guys on another slide. So the 8 ball, let me draw this ball again, went in this direction with a momentum of 8 kilograms times meter per second. Now the cue ball, remember, whenever you add vectors, you connect them head to tail, would be right there, and it went in this direction with a momentum of 2 kilograms times meter per second. Now again, whenever you're doing this on graph paper or trying to figure out these things, make sure you draw these to scale. For example, this vector right here would be 8 inches, and this vector right here would be 2 inches or centimeters. As long as they're to scale, it doesn't really matter. Now again, what we need to do is, in order to find the sum of these vectors, you take the tail of the first one and draw a line to the head of the last one. So this right here would be your resulting vector. Now if we went ahead and measured that, we would end up with 10 kilograms times meter per second. Now of course I know that this is not the proper angles And this, of course, if we actually measured it, it would not be 10 centimeters or whatever. But that is how you can use vector addition to add up and prove the law of conservation of momentum. And again, like I said, I know that since 8 plus 2, this is not in a straight line, then it wouldn't actually equal 10. But whenever you're figuring this stuff out, you're going to get different values than 8 and 2. But the important thing to remember is you're always going to end up with this momentum. Now, instead of just, adding arrows for fun, what this does, like I said, is it proves that the law of conservation of momentum is valid using vector addition. So basically the total momentum of the two resulting vectors equals the initial momentum. So there you go. So thank you guys for watching. Hopefully you'll understand now. And in the next video, I'm going to be taking the gun and the bullet problem to a whole nother level. So again, thank you guys for watching. I'll see you in the next video.